So we know that charged objects, when they're close together, they will exert a force on each other. And we can find that force using Coulomb's law. But how do they actually exert that force on each other? Because, as we know, they're not actually touching in any way. So one way to kind of explain this is to say that if we have a charged object, then it creates an electric field around it, and then that electric field can then exert a force on other charged objects within the field. So, in a way, a charged object does not actually directly exert a force on another charged object, but instead it sets up this electric field, and then that electric field then exerts a force on the other charged object. So if we have, let's say, we call it a source charge, which is just a charged object that creates an electric field. So we can see how strong that electric field is by putting positive test charges in the field. And we use the test charges to see how much force the electric field exerts on the test charges. So by Coulomb's law, we know that the force that a charged object feels is directly proportional to the charge of the object. So if we have a test charge with a charge of plus q, then let's say it will feel a force of F. And then if we put another test charge that has a charge of 2q, it will feel double the force, 2F. And so, if we have a test charge of 4q, it'll feel quadruple the force, or 4F. But this ratio of the force that a test charge feels divided by the charge of the test charge will stay the same for any test charge we put in the electric field created by this source charge. So we call this ratio of the force over the test charge the E field, or the electric field. And the E field is a vector quantity. So it points in the direction that the force would be exerted on a positive test charge. And so the E field is defined as the force that a test charge feels divided by the charge of the test charge. And replacing this F with Coulomb's law, and then canceling out the little q, we find that the magnitude of the E field at a distance away from the source charge will be k, the charge of the source charge, divided by squared. So at any point in the electric field, the magnitude of the E field does not depend on what test charge we put there. It only depends on the distance from the source charge and the charge of the source charge. And from here we can see that the unit of the E field is newtons per coulomb. And so we used positive charges to create this definition. So the E field always points away from positive source charges, and if we have a negative source charge, the E field will point into it. So to represent the E field in a region, we can draw what's called E field lines. And these lines are basically representing a lot of little E field vectors. So if we put a test charge somewhere here in this electric field, then it would feel a force that is in the direction of these E field lines. So the E field lines begin on positive charges and they go out from them, and they kind of flow into negative charges. And the more lines that come out or go into an object, the bigger the charge that it has. So for example, this one has 8 lines going into it, So if we doubled the charge of this negative charged object, then there would be, more lines, 16 lines going into it instead of 8. And the denser the lines are at any location, the stronger the E field is. So for example, over here, right next to the charged object, the E field will be much stronger than it is out here. So just like any vectors, force vectors, we can, if there are multiple electric fields, then to find the total E field at a point, we just find the vector sum of all the E field contributions. So let's say we have two charged objects, one positive, one negative, and they both have the same magnitude of charge, and then they form an equilateral triangle with this point A. So we want to know what's the total E field at point A. And we're giving this D here, and this is also D. And so the distance between each charged object and point A is So to use the formula, we first need to write this distance in terms of D. So by the Pythagorean theorem, 1/2 D squared plus D squared is equal to squared. So we can solve that is equal to square root 5/2 times D. And the magnitude of the E field contributed by both of these charged objects will be the same, since they have the same charge and the same distance from point A. The only thing that's different is the direction that they will point in. So we can go ahead and calculate the magnitude of the E field due to each charged object. So k q over r squared, plugging in the charge of the source charges, which is just the q, and then plugging in this expression for we can solve that the E field contribution from each charged object will be 4kq over 5d squared. So now we need to consider the direction. So here's point A, and remember we use positive test charges when we're dealing with electric fields. So assuming we put a positive test charge at point A, the E field from the positive charge, the E field points away from positive charges, so it will point this way. And the E field points towards negative charges, so it points this way when we're at point A. So notice how the Y components of these electric fields cancel each other out, and we're left with just the X components. So now we need to find this angle in order to find the X component of each E field vector. So the tangent theta, now theta here is equal to the angle over here, and the tangent of this angle is d over 1/2 d, or just 2. So solving for this angle using the tangent, we get that this angle is 63.43 degrees. So now the X component of each of these E field vectors will be the cosine of this angle times the magnitude, which we found earlier. So we solve for that, and then they both contribute the same X component. So if we double this, then we'll get the total E field at point A, and it points straight to the right. So let's say we have these two charged plates that make an electric field, and we have a ball that goes through the plates. So the ball has a mass and charge of this, and initially it's moving 40 meters per second in the x direction only. So we know that since this ball is a charged object, when it passes through this electric field, it will feel an electric force. So we want to know what is the deflection that it will experience in the y direction when it passes through this electric field. So the ball is acted on by both gravity and the force from the E field. So the net force will be mg plus qe. Because to find the force that a charged object feels in an electric field, we multiply the magnitude of the E field times the charge of the object. So then we can solve for the acceleration that the ball will experience by just plugging in all these numbers. And so we get the acceleration is 6,100 meters per second squared down. So now we find the time that it will take to pass through the plates, because it does not accelerate in the x direction. So we can just use distance equals rate times time to find the time interval. And the distance is 0.01 meters and the velocity is 40 meters per second. So it will take this much time to pass through the electric field. And then we can just use d equals 1/2 at squared in the y direction, since we found the time interval and the acceleration, to find the y displacement. So passing through the electric field, the ball will go down a little bit.